So good afternoon, students. In today's lecture, we'll go into the details of the CDF, which is the cumulative distribution function. But before going into the details, let's quickly recap what we had done in the previous lectures. So one of the previous lectures was on the introduction, and I explained you what is meant by randomness and why are we studying about random variables and random processes. And then I've still not told you why we are yet to study linear algebra, but as when the time comes, I'll tell you why we are also studying linear algebra in module 4 and 5. So let us keep ourselves engaged to only the random variables and process part right now. Okay. So having said that, we move to random variables, and here I had explained you that a random variable basically you can take an example of a signal as a random variable, and by now I'm sure you know what a signal is. So signal is nothing but an entity, let's say some m, which varies with time, right? So that is basically a signal, and since this m, the value of the signal, keeps changing with time t, we say that the signal is random in nature, right? So then we discussed what this random variable is, and we took the example of coin tossing, and we discussed that when we toss the coin, the outputs that we get or the observations are either heads and tails, and we say that the probability of occurrence of each of them is 0.5 because there are only two observations, and since the total probability is 100% of one, each of the observation, that is head and tail, will have a probability of 50% of 0.5. So from that logic, we can understand what a random variable is. So I've drawn the diagram for you here. So you can see that if we have a sample space, which is this cloud-like thing here, if you have the sample space, and within this sample space, we perform the experiments, right? So the experiments cannot be outside this sample space, right? So if we are tossing the coin, it's not that we can also choose a card, or if we can choose the color of a car. We cannot do that. So all the observations and the experiments have to be inside this sample space. To denote the observations, I have chosen small a, b, and c here, right? So each of these, that is a, b, and c, here are the observations, and you can see here that each of those observations are being mapped to a real number line. So if you see this xa, xb, and xc, these are nothing but the numbers on a real number line. So here we need to understand very clearly that the observation of an experiment is not a number. However, for our applications and our ease, we give them or provide them with numbers based on probability, right? So how do we do that? You have, if you concentrate on this observation A, we take this A and we say the random variable is capital X, and random variable capital X becomes a function of this observation or the outcome of the experiment, and that is mapped to a number X subscript A, right? Likewise, the experiment, the outcome B in this experiment in the sample space then becomes a function, or it makes the random variable X a function of itself, that is X of B, and it is mapped to a real number XB on the real number line, right? So that's why I've written this. So capital X is your random variable, capital X here is the random variable, B is the observation, and XA, XB, XC, which are subscript, X subscript A, B, and C, these are nothing but the numbers on the real number line, right? So the book specifies this example. However, before explaining this example, I had explained you about the coin tossing example, and I'm sure that was much easier for you to understand, right? So if you convert this into a coin tossing experiment, it will just have this cloud-like sample space here. It will have two outputs, heads and tails, and you will map them each to 0.5. Right? That will be the difference, right? So basically, overall, what we are doing with random variables is we are getting an output after conducting an experiment, but we are not keeping the outcomes as such. We are actually providing numbers to those outcomes, and we always deal with probability in the case of performing an experiment. So since probability is between 0 and 1, the outcomes should also be somewhere between 0 and 1, right? So after this, we move to a very important concept called CDF, which stands for the cumulative distribution function. So let me write that here. Cumulative means total, distribution function, right? And it is given as fx of x, where f is capital, x in the subscript is capital, and small x is the function, equal to capital P, which is denotes the probability of capital X, that is the random variable, less than or equal to x. So basically the CDF is a function of small x, that is the number. So what does this PDF basically denote? It denotes, or it tells us about the probability of outcomes in a sample space, such that the observation in the sample space is less than or equal to any real number, right? Now, obviously, this real number cannot exceed 1, or it cannot be less than 0, because it is a probability, right? So therefore, basically what CDF is telling us is this. Okay, so if you pay attention to the graph, you will really understand what CDF tells you. And if you remember or recollect, I had told you that CDF is a staircase function, which I have written here. And I had asked you to find out why it is a staircase function. I'm assuming that you have done that. If not, this will give you the answer. So if I have fx of x on the y-axis, and if I have these numbers x on the x-axis, then for each of these numbers, that is x1, x2, x3, and let's say x4, the CDF gets a value. So for x1, let's say this is the value. For x2, let's say this is the value. For x3, this is the value. And for x4, that is the value. So you can see here what is happening. When I reach x2, x2, let me use a different color. When I reach x2 here, the answer which I get, that is the value, this value here, which I get, is not only the value of fx of x at x2, it is also the value which occurred at x1. That means the value at x2 is the value at x1, that is this value, plus the value at x2. Similarly, when I reach x3, the value at x3 is not only the value at x3, it is the previous value, that is x1 and x2. So I get that. And then finally at x4, the same thing happens. And since we are dealing with probability, this axis, the y-axis, is between 0 to 1, right? So now you can view here how this CDF is helpful. If I need fx at x2, if I need the value fx at x2, what will be the value? It will be fx at x1 plus fx at x2, right? So at x2, it is cumulating or adding the previous values, right? So if I don't do the CDF, then it is very difficult for me to find the outcome at x2, x3, and x1, right? I can always find the final value because I know that probability is always going to be between 0 and 1. But at each point, x1, x2, x3, I will not be able to find the value, right? So CDF, cumulative distribution function, helps me in finding the probability values or the occurrence of the outcome at smaller values like x1 and x2, right? And why is it called cumulative? As you can see, I'm using this addition sign. So I'm cumulating, I'm adding. And why is it called distribution? Because you can see that this graph is distributed over x1, x2, x3, and x4, right? So it is cumulative distribution, and obviously a function because this fx is a function of this small x, right? So that is the advantage of using the CDF, right? Once we solve numericals, you will understand even more advantages of the CDF. So let's just wait for a few more minutes to solve the numericals. I will give you the properties of the CDF the best way to understand the properties of CDF is to solve the numericals and understand them, right? So this is a very common VTU exam question in the paper. What is CDF? Explain the properties of CDF followed by a numerical. Okay. So let us look at the properties of CDF and then we'll move on to the numerical. Okay. So the first property of CDF is if x is infinity, that is small x is infinity. So in this graph, if this x becomes infinity, then fx of x will become fx of infinity. And what will be this value? Anybody? What will be this value? Can anyone tell me what will be the value here? What should be the final value of this CDF? Look at the graph. What should be the final value of the CDF? Anybody?
1.
1. So fx, if x is infinity, that means x can have any values. Here in our example, we have taken 4 values. X can be till infinity, it doesn't matter. But the final value of fx of x, the CDF, is always going to be 1, right? So that's the first major property. So if in solving the numericals you exceed 1, then you have gone wrong. It's like probability exceeding 1. That's never going to happen, right? Okay. Now, on the same lines at the opposite end, if x is minus infinity, then what is going to happen? Fx of x will be fx of minus infinity. And what will this value be? Anybody? Huh? I couldn't understand. What will this value be? Fx of minus infinity? Anyone?
1 only, sir.
1 only. What does fx of minus infinity mean? X as minus infinity means I have not performed any experiment only. The x as infinity means I have performed all the experiments. So when I have performed all the experiments, what will be the total probability? 1. But x as minus infinity implies I have not performed any experiment. So what will be the answer to that?
0.
Yeah, that means it is the initial value. So in the graph here, this is the value. So x as minus infinity is here and x as plus infinity is here. So the final value is always going to be 1, but the initial value is always going to be 0, right? So this answer here will be 0. Third property. Okay. Now, if x is between minus infinity to plus infinity, then what would be the range for the CDF? What should I fill? What should I write here? What should I fill here and what should I fill here? Look at point 1 and 2. If x is between minus to plus infinity, what will happen to the CDF?
0 to 1.
0 to 1. Because when x is minus infinity, the CDF is 0, that is here. And when x is plus infinity, that means all the experiments have been performed, the value of the CDF is plus, right? So that range is very, very important. The next property is CDF is always increasing function, or as already discussed, a staircase function. So I already explained you why this is a staircase function, right? Now, next property which is going to be very helpful for us in solving the numericals. The probability if x is between two values, x2 and x1, if this is given to us, if I want to find the probability of an event between two values x1 and x2, then I can use the CDF to find the values. And you can see here, if I go back to the graph, if I want to find the probability between x1 and x2, right? If I am lying here between x1 and x2, then what should I do? I should get the value of CDF at x2. I should get the value of CDF at x1. And since it is cumulative, if I subtract the two, I will get this probability. Right? I'll repeat again. If I want to find the probability of an event between two values x1 and x2, right? I find the CDF at x2. I find the CDF of at x1, and then I subtract the two values so that I can find the difference between x1 and x2. Right? So that is exactly what we can do here. If I want to find the probability between two values x1 and x2, then it is nothing but fx of x2 minus fx of x1. Right? This is a very, very important property. It will help us a lot in solving the numericals. Okay. Next is not a property. It is already something we have established, that CDF starts with 0 and ends with 1, right? Because it's a probability value, right? The next is going to be helpful for us to discuss the PDF, that is probability density function. But I'll just state the property here. We'll discuss this later. If I find the derivative of fx of x, then this is always greater than 0. That is, CDF is non-decreasing. Okay. So I'm not explaining much about property 6 right now, because we'll be dealing with this derivative of the CDF when we talk about the probability density function. So I will be explaining you that at that time, right? Now, since random variables can be continuous, discrete, or mixed, like which we had discussed, continuous random variable, discrete random variable. Likewise, CDFs can also be continuous, discrete, or mixed. Okay. Again, this I will be discussing a little later on. Right now, let's pick out some numericals. Once you solve numericals, you'll be able to understand these properties much better. Okay. So let's see how we can use these properties. Okay. So I'm hoping that you all are sitting with a pen, paper, and pencil, and not just listening to me, because if you start solving, you'll really understand. Okay. So the question is, so this is let's say numerical 1. CDF of a random variable x. CDF of a random variable x is, okay, so this is how it's given. Fx of x is equal to 1 minus exponent minus x square by 4 minus x square by 4, and this happens for x greater than or equal to 0, and then we have a value 0 for all other cases. Okay. The question is evaluate probability of 1.1 less than x less than 2. So what would be the solution here? So if you take this probability of 1.1 less than x less than 2.1, we know that from property number 5, that if I want to find the CDF between 2 points x1 and x2, it is nothing but the CDF of the higher point subtracted with the CDF of the lower point, right? So in this case, we can view, let me make a mark, we can view this as probability of x2 less than x less than probability of x1 less than x less than x2, right? So now if I want to find the CDF, let me take this pen. So in this case, or let me write it in this format. So probability of 1.1 less than x less than 2.1 will be nothing but the CDF of x2 minus the CDF of x1, right? And we know what the CDF is because the CDF is given to us, right? So it is 1 minus exponent of minus x square by 4 for x greater than or equal to 0. That means this CDF exists only for values greater than 0. For values less than 0, it does not exist, right? So what will happen here now? What is the value of the CDF? The CDF value is 1 minus e raised to minus x square by 4, right? So instead of this value here, now I can write this as 1 minus exponent minus, instead of x square, now I will write x2 square by 4 minus 1 minus exponent, instead of x square, minus x1 square by 4, right? Therefore, now I can write this as 1 minus exponent. Now what is the value of x2? The value of x2 is 2.1. So you'll have 1 minus exponent of minus 2.1 square by 4 minus 1 minus exponent. Now what is x1? x1 is 1.1. So minus exponent minus 1.1 square divided by 4. Right? So very simply, now we can simplify this. You'll have 1 minus exponent minus 2.1 the whole square by 4. Now I'll open the bracket here. So you'll have negative 1. Negative into negative will become plus exponent 1.1 the whole square by 4. Right? The 1 there will cancel each other. So you'll be left with, now I'll just write with in the other format. So you'll have exponent 1.1 the whole square by 4. There should be a negative here, minus exponent of minus 2.1 the whole square divided by 4. Okay. Now, can anyone use a calculator and let me know what is the value? Let me know, someone, what value you get. Let me know this value here and let me know this value here. Are you telling me the total answer?
Yes, sir.
Okay. Even I have 0.409. Are you getting that?
Yes, sir.
Okay, great. Okay. So the calculator will help you in getting that answer quickly. But what is important is the method to find it, right? So the method is very simple. If we have uh, the range given for the CDF, and if we want to find the probability between that range, then it is nothing but the the CDFs at the 2 points subtracted with each other. Okay. Now, just for your practice, okay, you can take probably a couple of minutes. I'll give you another numerical. Please try it out. So let me give you this. Okay. So the CDF of a random variable z is f z of z, small z. I'll not use this small z. It has confused students before, so I'll use this z here. Okay. And this is equal to 1 minus exponent of minus 2 z raised to 3 by 2 for z greater than or equal to 0 and 0 for all other values. You need to evaluate probability between 0.5 and 0.9. Okay. Please do this yourself and let me know what answer you get. Follow the same process. After you finish, I will also be doing it. So please take a couple of minutes, follow the same procedure like the last numerical, and let me know what answer you get. Okay, so I'm hoping that you are able to do this. So now I'll proceed with the solution. Uh, so we need to find the probability between 0.5 less than z less than 0.9. And to find this probability, this will be nothing but the CDF between 0.9 subtracted with the CDF at 0.5. Right? So let us calculate this separately because we are given it in the form of an exponent. Right? In fact, this should be z because the random variable is z. Okay. So let me take fz of 0.9 and fz of z is 1 minus e raised to minus 2z raised to 3 by 2. So this will become 1 minus exponent of negative 2. Z will become 0.9 in this case raised to 3 by 2. And the other factor, which is fz of 0.5, will be 1 minus exponent of minus 2.5 raised to 3 by 2. Okay. So This answer that I have is let me check with me, okay? 0.8187. Is anyone getting this answer? And this answer that I have is 0.50693. So the total probability between zero point 0.5 and 0.9 is 0.8187 minus 0.50693. So I get somewhere around 0.4069. Is anyone getting this?
So I'm getting 0.3117.
I can't hear you clearly enough. Let me see. I can't hear you properly. One second.
0.3117.
0.3117. Just type in your answer on that message. I'm not able to hear it properly. Just send in a message on that Teams. What answer you get? There will be some approximation because it's an exponent. Let us see what we get. If it's around 0.39 or something, it's okay. Somewhere between 0.39 to 0.4 is okay. That's fine.
Even if you subtract your answers, I'm getting the same.
You are getting the same? Okay, good. If it's the same, it's fine. Because it is an exponent, it will be some approximation in the calculator as well. So if it's between 0.39 and 0.4, then it's fine. Then nothing to worry about. Okay, but I'm more interested in the process part. So I think the process is clear. Any doubts on this? Anybody?
No, sir.
Okay. Yeah, your voice was clear. I don't know why the other voice was not. So is are you getting 0.40 or 0.39 something? Everybody?
9, sir.
Yeah. Okay. Then that's fine. I'll just leave you with another question. It's just a similar question, but you can just try it out. So let us see. Or let me just move ahead and then we'll do the CDF part a little later. Okay. So this is as much we need to know in the CDF part. So just a quick recap of CDF. Uh, so the CDF is nothing but finding the probability value at each of these random variables, and we then accumulate or aggregate or find the total of the probabilities at each of these outcomes, that is x1, x2, x3, x4, and hence the total probability is always 1. So we have discussed the properties of the CDF. So x at infinity will give you 1, at minus infinity it will be 0. The most important property is uh, if you want to find the probability between 2 points x1 and x2, just take the CDF and find the subtracted value between the higher value and the lower value. That will give you the CDF, right? Okay. So now let's move to the next part. Again, we'll be coming back to the CDF every now and again because module 1 and module 2 are based completely on CDF and PDF. Okay. But let's quickly look at what this idea of PDF is. So the next idea we are going to discuss is in short known as PDF, which stands for probability density function. Please do not confuse CDF and PDF and their full forms. CDF is cumulative distribution function because we are finding the total and then we are distributing the probability as well. PDF is a probability density function. So basically with the PDF, we want to find, or we wish to find, what is the density of the probability. Means how much of probability is higher at a particular place or how much of probability is lower at a particular place. That's why it is the density, right? So it's like population. Sometimes we want to find uh, which state or which city has more population, which has lesser population, right? So like that we wish to find what is the density of the probability at a particular place, right? So just to give you an example, an application of PDF is actually to find the population of a country, right? So we are always able to find the uh, density using the density function. We are able to find the population of any city or any particular country, right? So let's see what this PDF is. So the definition of the PDF of a random variable actually comes from the CDF itself. So the PDF of a random variable X is, we denote it as small f as opposed to the capital F for CDF. So please keep the same nomenclature. So you have small f, capital X of X, and this is equal to d by dx, that is the derivative of the CDF, right? So that's what I told you in point property 6 of CDF, that we'll discuss this in PDF. So that's how we are able to find the PDF value, right? So the PDF is nothing but the derivative of the CDF. On the other end, if we do the opposite process, we can find the CDF by integrating the PDF. This is a very important property. Of course, I'm not writing the limits here, but there will be limits. I'm just going to put some x because we are dealing with random variable x here. Right? So these two are very important equations for us, and the whole of random variables is basically going to be dependent on these two equations. Okay, you also have the equation for CDF, but mostly it's going to be the PDF that we are going to always use, right? So this PDF is always a non-decreasing and a non-negative function, and therefore the limit here is always starting. The limit here always starts with a minus infinity, right? Because below minus infinity we are not performing any experiment, right? Because at minus infinity the value of CDF is 0, so going below this minus infinity does not make sense. So we are performing the experiment starting at minus infinity and going to some x, right? What is the value of x, we do not know, right? So as you can see, we can find the CDF using the integration, or by integrating the PDF, which basically implies we are here finding the area, right? Because as you must know that integration is nothing but summation of finding the total area, right? Now, going by the logic of integration, if I take this integral value on the RHS and write this as minus infinity to plus infinity fx of x dx, what should be the value? Anybody think what should be the value? See, what does this equation denote? The lower limit denotes that I'm starting the experiment. The lower limit, that is the lower value of the limit here, minus infinity, denotes I'm starting the experiment. The highest value, which we had put as x, I have just stated it as infinity, which means that I've completed all the experiments. And then I'm using an integral. That means I'm summating all those values, right? So when I summate all those values between not conducting an experiment and conducting all the experiments, what should be the value? Anybody? When you don't conduct any experiment, the value of probability is 0. When you conduct all the experiments and sum them, what should be the value?
1.
1, right? So basically this answer will be 1, right? Because if you see here, if you see how it is related, integral of the PDF, this side here, integral of the PDF is nothing but the CDF, right? And what is the total value of the CDF? The total value of the CDF lies between 0 to 1. The final value is always going to be 1, right? So we are saying the same thing in a different form. So again, we are saying that the total probability is only going to be 1 for the conduction of an experiment in two different formats. One in the form of a CDF and the other in the form of a PDF, right? So in CDF, we are done fx of x2 minus fx of x1 to find the probability. Here we are finding it in the terms of area, right? So this is what you would read in the book or over any website. Total area under a PDF is always 1, right? That makes sense because the total value of the probability is never going to exceed 1, right? So this is a very, very important property. It's actually a property. It's a very important property. So what we'll do now is we'll just look at the properties of the PDF and stop there. And next lecture tomorrow, we'll start with the numericals on PDF. We'll completely be able to understand how this PDF will be much helpful to us as compared to the CDF. Right? So majority of the numericals will be based on PDF rather than CDF. Right? So let me give you the properties of PDF. Please go back, revise them, and then attend the next lecture so that you are familiar with the terms which I am using. Okay? So the first property is PDF is always non-negative, which implies fx of x is always greater than or equal to 0. Okay. Please also understand the difference between how CDF is written and PDF. PDF is in smaller alphabet. CDF is in a capital alphabet. Right. Next is the total area under the PDF is equal to 1, which we have already done. So I'm just writing the equation minus to plus infinity fx of x dx is always going to be 1. Third property, if you have or if you want to find the probability at a particular point, only that point, that will be nothing but x to x fx of x dx, and the value, because you can see the two limits are the same, this answer will be nothing but 0, right? Which basically implies that probability of random variable equal to any specific value x is always 0. Okay, this is an important property. The most important property is property 2. Okay. So third property tells you that probability of random variable equal to any specific value x is always going to be 0, right? Then we have a fourth property. If you want to find p of x less than equal to x, or p of x less than x, this will be nothing but fx of x, which is the CDF, and this can be written in the terms of PDF, which will start from minus infinity and go till this value x here, right? And if this value x happens to be plus infinity, this integral value will just become 1, right? So again, the PDF is giving us the total value or total area under particular points. It is giving us the density, right? That's why it is known as the probability density function. So the next property is which we have already written. Fx of x is the derivative of the cumulative distribution function, and vice versa, that is fx of x, that is the CDF, is an integral value from minus infinity to plus infinity of fx of x dx. So this is not a property, this is something which we had done already. Right? So these probability PDFs are very helpful in calculating many statistical parameters. We'll be able to find things like average value, variance value, correlation, uh, autocorrelation. Uh, I think you would have done variance, standard deviation. These values are can be found very easily by using the probability density function. Okay, so we are going to see how we can find these values using the probability density function. Okay, so what I would urge you to do is just go back and see whatever we have done in this lecture. So tomorrow's lecture we are going to solve numericals based on the probability density function, and then we'll also be looking at if uh, the random variable is discrete in nature, right? Then we cannot use the PDF because it uses an integration sign. In that case, we use what is known as a probability mass function, PMF. Okay, so this is also something that we are going to look at tomorrow, and then we'll see how we can draw these probability mass functions as well. Okay, so attend the lecture tomorrow. We'll be able to solve many numericals based on that. Okay. Okay, so I think the time is up for today's lecture. So I'll see you in tomorrow's lecture. I'm trying to post the videos on YouTube as well. So I think by tomorrow I should be able to do that. But these lectures are available to you on Teams, so you can always download and read. Okay. Please read and please read or solve and come back tomorrow's lecture. It will help you in understanding better. Okay. So I'll see you in tomorrow's lecture.